Okay, so we're applying Hooke's energy law to bungee jumping, and what we have is a bridge, and under the bridge there's some water. And every bungee jumper likes to do their jump above water unless they're really risk takers, but we're not going to be too risky here. We're going to say that we're above the water and ready to jump, and a few things to set up the problem. I'd like to say that the bridge is about 100 meters, 100.0 meters above the water. Okay, so this person is jumping from 100 meters up. The other thing that I want to claim is that the bungee cord, and I'm just going to show the bungee cord lying loose but not attached to anybody, this bungee cord has a length of 15.0 meters if it's just hanging slack. Okay. I also want to say that there's an elastic coefficient, a spring coefficient if you want to call it that, of 70.0 newtons per meter for the actual bungee cord. And we'll say that our person has a mass of, a nice round value, 75.0 kilograms. Well, we've said before that we could talk about conservation of energy using more than just gravitational potential energy and kinetic energy. In other words, what we've said in the past is that E total equals Eg plus Ek. And what I want to propose now is that if I fall down, or if this person falls down so that they get anywhere past the end of the slack in this bungee cord, what type of additional energy is going to get thrown on top of their Eg plus Ek? Yeah? Yeah, elastic. I'm going to call it spring energy, but it's elastic potential energy. Okay? So let's just go through very quickly. I'll bring in an extra piece of paper so we can map this out. I want to talk about the fall. So as this person falls, here's our bridge again. As the person falls, when they start off at the top, that's one critical position. When they just get to the end of the rope, that's another critical position. On their way down, I won't say it's a critical position, but it is a position. And then at some point, they're going to come to a stop. Let's just assume that they don't hit their head. Because it's always thrilling if you don't hit your head, but you come close. I guess if you do hit your head, it's thrilling, but it's over quickly. Okay, and you're thankful you bought the insurance. Anyway, so critical points. Let's number it up. 1, 2, 3, and 4. And I've already explained what the critical points represent here. But I want to talk about the actual total energy equation. E total equals, for situation 1, E total equals Eg plus Ek plus Es. Situation 2, same equation. I'm going to actually ask you to write it out. And 3, and 4. Now, the reason I wanted to write this equation out 4 times is so we could talk about where things become zero, or where they become maximized, or what have you. We're going to assume that there's no air drag or anything like that. Same assumptions that we commonly make with these problems. Let's take a look at the first equation. Does anything zero out in the first scenario? Yeah? I think Ek zeroes out. We haven't jumped yet. Yeah? Yes, yeah. In other words, E total is equal to gravitational potential energy. That's actually a good starting point, because one thing that you can be sure of is that we start at a particular height, and if I know that value, I know the total mechanical energy. And if we're not talking about drag, then we don't have to deal with efficiency issues or anything like that. We can just know, starting off, what the E total is to start with. All right, the next one. When I get to the end of the bungee cord, is there anything that zeroes out? Yeah?
Yes.
Yes, yeah. Now, something that I want to point out is that if I know how long the bungee cord is, I also implicitly know how far I am from the ground. Can you all see that? Which means that if I know the length of the cord, then Eg is findable. That's important. Okay, so I want to make note of that. if I know, oopsie, bungee length, I'll just call it, EG is findable. That's kind of useful information. Okay. Yeah.
How come the spring energy is cancelled out?
Oh, because I said that point 2, when we defined this little scenario to start with, I said that point 2 was the length at which they just get to the end of the rope. Just get to the end of the bungee. Hasn't started to stretch the bungee yet.
Okay.
So scenario 2 is when he hasn't started to stretch the bungee yet. And if I know how long that bungee is, then I can subtract that length of bungee cord from the total height, which was this height, and that'll leave me with my new height, and that'll let me find the EG value. So EG is findable if I know how long the bungee cord is. Since that's findable, and since E total is conserved according to what we've said previously, with roller coasters and whatnot, is EK findable? Sure. Okay. Let's go on to the next one. Scenario 3. I'm in mid-fall. Does anything zero out? Everybody shakes their head. Okay, nothing zeroes out. Is there anything that we know? ET. So there's things that we need to be told here. We need to be told how high I am above the ground at that particular point at point 3. So I need to be told this information, how high I am above the ground. But the thing is, if I'm told how high I am above the ground, then I could do some subtraction and I could figure out how far I am below the bridge. If I know that the bridge is 100 meters above the ground, for example. And if I know how low I am below the bridge, and I know how long the slack bungee cord is, could I figure out what the delta x value is? Okay, so there's some logical steps that go on there. So I'm going to say that all this stuff would be findable, but we must know either the height of the person, or the height they are off the ground, or the delta x value in order to actually fill in all the other blanks. I need to know those two pieces of information. Okay? Yeah? If I knew the velocity? Yeah, you're right. If I knew the velocity, then I could do some things with that as well. Sorry, I was just thinking about the physical geometry measurements, but you're right. Alright, the last scenario. Let's see if there's anything that I could zero out here. Yeah. Kinetic energy. That's when they come to a stop momentarily. I like that. Now, I'm not going to claim that EG is 0 because I don't want to set up every bungee cord scenario where I have to hit the ground. That's just dangerous engineering right there. So I don't want to say that I want to zero out the EG. I mean, perhaps you want to come within a few feet of hitting the ground, but you definitely don't want to actually hit it. So that's irresponsible use of a bungee cord, I suppose, whatever you want to call it. The E total is given to you, and again, I would need to know either how far I've stretched the cord or how far I am above the ground to get my EG and then my ES. Okay? So again, we need to know some of that information to solve the scenario 4 problem as well. Does anybody have a question about that so far? Okay. So I'm going to pause it there, and I want to start